We're from Wilchen Incorporated, and today we're here to talk about our Heracles processor. I'm Anthony.
And I'm Qing. And today for the agenda, we're going to briefly discuss about our company and our processor. We're then going to go into the baseline, the architecture, the enhancements, and any of the future plans. We're then going to end the session with a Q&A.
So our company is named after our two founders. It was their cooperation that enabled us to get where we are today, so they're pretty important. And our processor is named Heracles after the Greek mythological hero. The name conveys a sense of power that is important to our processor, and we chose the name the Greek Heracles rather than the more common Hercules, just to differentiate us on the market.
Here's a little something about our processor. It's a hardware architecture. It has 32 64-bit integer registers and floating point registers. It has a 32-bit flag register, and our memory structure is a 1024 by 32, meaning every memory structure has 32 bit, and we have 1,024 locations for memory. And when we load and store into memory, we use Little Endian format, and we have 3 addressing modes: the immediate, register, and register indirect.
Our instructions fall into several different formats. All formats have an 8-bit opcode at the start, but the way they address their information is different. First is the triple operand instruction. It uses 3 registers, and it has to address them, it has 3 5-bit register addresses called source 1, source 2, and destination. And in the assembly code, we order it in the same order as the information here. So operation, then source 1, then source 2, then destination. Double operand is similar, but unlike triple operand, it will only use 2 registers at once. And going even further, there's the single operand instruction, which has no possible source 2, only source and destination. Getting away from register use is the conditional jump instructions, which, if the condition is found true, will use a 24-bit sign displacement added to the instruction pointer to change the current location in the instruction code. A different type of jumps are the unconditional jumps. Some of them also use the 24-bit displacement. However, others can use a register address, and the information within the register is substituted into the IP to jump. And the return instructions, the return instructions don't use any information. They're simply all zeros. This is a format that is also shared with the flag and crosser instructions, which are, again, zeros. Getting back to register use is the immediate instructions, which use a source register and a destination register. However, instead of a source 2 register, they have an 8-bit immediate value that is used in its place. And finally, we have the floating point instructions, which go back to a source 1 and a source 2 and a destination register, with the difference being that these point to floating point registers rather than integer registers.
Mm-hmm.
Here is a little about our architecture. We have the CU and the CPU EU, and we have 3 memory modules down here. All 3 memory modules are pretty much the same, except for the I/O module. The I/O module will do a handshake with the CU, which is when I/O has given the CU an interrupt, the CU will then take that interrupt, set up its interrupt states, and then return interrupt acknowledge, which will tell the I/O to stop sending the interrupt. This is the original graph that we based our CPU EU off of. Here is our CPU EU. We still have the floating point data path, the integer data path, and the bus interface unit. A few things we added were the 3 muxes up here for register addressing, and a DX mux right here. The DX mux will input 64-bit 0 for enhancing instruction we did for clear register, a sign extension of IR1520 for the immediate operands, a rebuff out for the the OR high instructions, and a sign extension of R out 2320 for the conditional jumps. Here is the original integer data path graph we based our integer data path off. I will go into these addressing muxes later on. As you can see, our integer data path is pretty much the same. We have the integer register file, the ALU, SMUX, and YMUX. We've added in a barrel shifter and a barrel shifter mux. We will go into that in more detail in our enhancement section. Here we have our addressing muxes. The reason we added these addressing muxes is because we found that it will be more efficient to send 1 or 2 bits from the CU to the CPU EU, because since the CPU EU already has the IR coming from the BIU, it will be more efficient if CPU EU would be grabbing the addresses instead of the CU and then sending it off.
Mm-hmm.
And here's our floating point data path. This is the original picture. Not much has changed. We still have the floating point register file, the XMUX, and the ALU. As you can see, we added the 3 addressing muxes up here. This is the original BIU graph, and then here is ours. We've extended the muxes down here for rebuff, write buff, and we added another mux for IP. For rebuff, we added in zeros for the load immediate and OR high immediates for rebuff, and then we also add in the reg out. The reason we add in the reg out is for the exchange instruction. We figured that since the BIU already has registers, we don't really need to implement another register inside the integer data path in order to contain the register that it's supposed to pass on. For write buff, we could take in the IP, the current status of IP. Whenever interrupt is called, we could load that address location inside memory. And we also have our flag register being loaded into our write buff, and that's also when interrupt is called. We'll load that into the thing. For our IP mux, we could load the IP with 32FF whenever interrupt is called. We also have rebuff out for exchanges. Sorry. We also have rebuff. We read rebuff for interrupt. Good. Whenever return frame interrupt is called, we will load the past IP address onto the IP. We also have reg out loaded into IP for jump route register instructions, and we also have the IP branch address for whenever we have a jump instruction being called.
So the biggest enhancement we made to our processor was the addition of the barrel shifter, which allows multiple shifts in logical, arithmetic, and rotate. We also added a clear register instruction, which sets a register to all zeros. Here we can see the formats for these instructions. The shift multiple has a source register, a destination register, and a 6-bit immediate amount that is the shift amount. And the clear register only has the destination register that is to be cleared. Here we can see the code for our barrel shifter. As you can see, we created a double-sized temporary register, which takes a concatenation of the input with another value relevant to the type of shift. And then the output from the barrel shifter is a selection from that temporary register that is equivalent to a shift of one less than the actual shift amount. it's one less because the final shift occurs within the ALU, which also sets the flags for the operation. Here we can see a demonstration of the principles of our barrel shifter. We've taken it down to only 8 bits just for simplicity. Here we'll be doing a rotate right by 6. Because it's a rotate, the temporary register receives a concatenation of the initial value with itself, and then it outputs a value equivalent to a shift right of only 5, with the final shift, the final 6th shift taking place in the ALU, which also sets the flags. The concatenation occurs differently for other operations, such as logical left, which places the initial value in the upper half of the temporary register with zeros in the lower half, and arithmetic right, which places the original value, the input value in the lower half, with the upper half being a repetition of the most significant bit of the initial value. Here you can see a demonstration of the efficiency of multiple shift compared to repeated single shifts. This is a snippet from our verification code. And this is a loop which performs 10 instructions to rotate a register right 3 times and then store the value. And assuming it occurs 5 times, that's 51 instructions plus the halt. However, if we had used the single rotates, that would have added a total of 4 instructions per loop for a total of 20 additional instructions, making the rotate multiple clearly a lot more efficient. And the clear instruction has several advantages to it as well. Compared to loading in just all zeros, the clear only has 1 state, so making it faster than the 2 states of the load immediate. And compared to using subtraction to clear a register, to set a register to zeros, it not only does just saying clear this register a little more obvious than saying subtract this register by itself, but clear also does not affect any flags, which could potentially be very important for your code, for the user's code.
For our future plans, we have gathered together and discussed about pipelining, but due to the time constraint that we had, we scratched the idea. But we will try to implement it in future. For our barrel shifter, when we look back into our code, we realized that it will be more efficient for us to use the Verilog operation of shift left and shift right with the shift amount -1 instead of using a temporary register concatenated with the value, because it will look simpler to the future users when they were looking at our source code. And also, another way that we'll optimize our barrel shifter is that instead of sending the value to the ALU and make the ALU shift 1 last time, we will optimize our barrel shifter to shift the whole amount and produce flags itself, and those flags will be sent to a MUX, which will choose between an ALU and the barrel shifter flags. Is there any question? Yes.
Going back to your exchange instruction, you go back into the VIU. You actually send the data back into your VIU into rebuff 0, correct?
Right. Well, rebuff 0 and 1 because we have
a 64-bit, right?
yeah.
Can you back one more slide, please?
Yeah.
Going back to your interior data panel. There you go. So where does that value go in?
That value will go into the rebuff here. Sorry. That value will actually go into dy right here, which will go into ymux and then load it back into the integer file, register file. Yes?
For the shifter is shift amount -1, that little snippet. That's because the AOU does the final shift?
Yeah,
Yes,
because
yeah.
we want the flags to be set when it's shifted. So one way we thought of was just to make the ALU shift it one last time, and then that way it will set the flags.
What was the reasoning behind using the ALU to do the last shift in your barrel for your barrel shifter?
Well, we wanted to set the flags for the operation, but, and when we were thinking, that was simply the first thing that came to mind, because the ALU is already setting the flags. It wasn't until later that we considered having the barrel shifter set the flags itself, and by then it was too late to make that change.
What did the other teams do? What did you guys do? How'd you set the flags on a barrel shifter?
We excluded them.
We didn't have the barrel
Oh,
shifter.
no flags. Oh, you didn't have a barrel shifter?
No, we had a barrel shifter, but they did set the flags. We had the ALU set the flags on the operation. So we had it in series with our ALU. So your value you wanted to use would go through the barrel shifter, be shifted, then have the ALU perform the operation. And then the ALU would set the flags based on that.
ALU perform what operation?
And if you wanted to do an addition, let's say, 2 registers.
Well, that's right, because they did a combined thing, like shift and add, kind of like an ARM. Whereas yours was the shift, and then you wanted to set the flags. This is not just for you, but for everybody to think about. When you say optimize, we're going to optimize. So optimize could be, like you mentioned, we want to make it easier for whoever's looking at our implementation. It's easier to see, kind of easier to recognize what we're doing. Versus how much resources used when you synthesize your Verilog code. So optimize means, you know, faster, smaller, versus easier to read kind of thing. That's something more on the surface. So I don't know, I do this all the time. I want to know, when I synthesize this, you know, how much of my FPGA resources is it taking, versus if I synthesize a different version that basically does the same thing, how much resources is it taking? And it's something you all should be thinking about and doing as senior level engineers, is optimization is faster, smaller, less power, of course. And so it'd be interesting to see. So, you know, you see how somebody else did it, and it maybe looks easier on the eyes, but maybe it takes more resources to do it that way. Because every statement we made, we talked about this at the break, it all gets synthesized. So if you use, you know, triple angle bracket, Verilog, arithmetic shift operator, what actually gets synthesized versus if you kind of extracted a carry and then did that type of operation. It's always interesting. You should all be conscious of, you're synthesizing Verilog code. So a lot of this is combo logic that we all did. You know, we just make Verilog statements based on the time frame. So optimization is not just, you know, the code being optimized, but this more important is what gets synthesized and how much resources it's taking. Then you do the timing. You can see how long that issue takes, how long this issue takes. But you guys did an excellent job of preparing. I'm very impressed. Great job. Yeah.